Okay, this lesson goes with 8.3a inverse functions. Notes for Algebra 2. Inverse functions have to deal with switching the domain and range. So in an inverse relation, it maps the output values to the input values. And so instead of inputting x's, you're inputting y's. It's like the x's and y's switch. To verify if functions are inverses, you must show that when you compose the inverse of the original function, it equals x. And if you take the composition, whoops, that's cool, I didn't know you could do that. If you take the composition of the function composed with inverse, it also equals x. So you have to do it both ways and show that they both equal x. So let's just review composition real quick. So f composed of g of x. Here's my two functions. I have f on the outside. So composition kind of looks like this. You start with the f of x, and then I want to put the g of x in there. So I replace the x with my g of x function, which is x minus 9. So then on this side, wherever I had an x, I now have the x minus 9. So wherever that x was, right here, I replace it. And then I'm going to simplify this one. Using order of operations, you have to square that first. So that's x minus 9 times x minus 9. So I'm going to FOIL that. I'm going to get x squared minus 9x minus 9x, so minus 18x in the middle. Negative 9 times negative 9 is 81. Then I have to distribute the 2, so 2x squared minus 36x plus 162 minus 5. So final answer, 2x squared minus 36x plus 157. Now this is a quadratic function, our new function, and so the domain for a quadratic function is all real numbers. All real numbers for the domain. So that, I just wanted to review the composition when you compose one function of the other. Remember that typically when you, or not typically, that if you take f composed of g of x, it is never equal to g composed of f. But we want to show with the inverses as if they are inverses, they are equal, and in fact, they're both equal to x. So that's what we're going to show. All right, so inverse functions map the x to the, or so the original relation takes x to y. The inverse relation maps y to x, basically. So the x and y switch. So for example, my first relation over here, I'm going to graph this. I have 0, 1, 2, 3, 4, 2, 3, 4, 5, and 6, 7. 6, 7. So here's my original relation, these points right there. So in my inverse function, instead of 0, 1, I'm going to have 1, 0. The x's and y's switch. Instead of 2, 3, I'm going to have 3, 2. Instead of 4, 5, I'm going to have 5, 4. And then instead of 6, 7, I have 7, 6. So it's going to look like this instead. You're going to have 1, 0, 3, 2, 5, 4, and 7, 6. Now you might notice a couple things here. One thing I want you to notice is that an inverse relation is reflected over the line y equals x. That's this line right along the diagonal. It has a y-intercept of 0 and a slope of 1. So notice how those points there are reflected over that line. Oh, I graphed the 0, 1 point wrong. That should have been right there. That's why it looks weird. So get rid of that point. All of these points then are reflected over that orange dash line. So an inverse is reflected over that line. Now for the original, the domain is the set of numbers that is 0, 2, 4, and 6. And then the x's. And then the range is a set of numbers 1, 3, 5, and 7. In the inverse, those switch. In the inverse, the domain is 1, 3, 5, and 7, the inputs. And the range is the set of numbers 0, 2, 4, and 6. So this is the function. This is its inverse. So it switches the domain and range, switch the inputs and outputs, switch places, and it also, on a graph, reflects it over this line y equals x. So if we graph the inverse, it is kind of hard if you were to just draw the line to try to reflect it. So like this point moves down here, this point moves over here. So it's hard to do that just by looking at the picture. So I like to get a couple points off the original. So like the point -1, 0. And then maybe this point right here, 3, 2. And then for the inverse, those would switch the x and y. So the inverse would be 0, -1, and 2, 3. So 0, -1 would be right here, and then over to down 3. And so the inverse would look like this. Maybe I need one more point. How about one in the middle? Like I have 0, 1 right here, 0, 1. So I'd have 1, 0. So 1, 0 right there. 2, oh, that's why I graphed this bottom point wrong. I'm sorry. You got to go over to up 3. It should be up here. That's why it was not looking right. And so it's going to look like that, the inverse one. So this piece of the graph here reflects, this piece reflects up here, and this piece reflects over here. So that's the green one I drew is the inverse of that. How about for the parabola? So I should have maybe graphed that down here. Maybe that's what this graph was for. 2, 3. There's the inverse. Okay, we'll graph the parabola one down here. So the original parabola, if I steal a couple points here, let's go with -2, 2, -2, 2, 0, -2, and 2, 2. And then for the inverse, those will switch. It'll be 2, -2, -2, 0, and 2, 2. So over 2, down 2, -2, 0, and 2, up 2. So my new inverse function will look like this. So this is the original, this is my inverse. The original, we call that f. F of x is my original, and f prime of x is my inverse. So we use this little -1 to denote that that's the inverse of the function. So how do you find the inverse algebraically? We looked at a table, we looked at the graph. To find it algebraically, you switch the x and y's, and then you solve for y again. So instead of y equals -3x plus 6, switch it to be x equals -3y plus 6, and then solve for y. So to get y by itself, I'm going to start by subtracting 6 on both sides. You get x minus 6 equals -3y, and then divide by -3, and we're going to get, we could either leave it like this, just x minus 6 over -3, or you could write it as, this is 1 in front of the x, so we'd have a -1/3 x for the 1 divided by -3, and -6 divided by -3 is +2 equals y. And this would be like y to the -1 power. This is the inverse function. So that's my inverse. switch x and y, remember that f of x is the same thing as y. So it's like having this, then replace, switch them, then solve for y. So subtract 4 from both sides, get x minus 4 equals 2y, divide by 2, divide everything by 2. This is a 1x, so it's a 1/2 x, and then 4 over 2 is minus 2. And so that equals f of negative 1 of x. This really isn't f to the negative 1 power. It's just this negative 1 out here just means that's the inverse. It's like the way to denote it. Just like we use this r for all real numbers, f to the negative 1 just means inverse. Okay, so it's just a denotion. It's not an exponent in that sense. So if I want to verify that these two are inverses of each other, so I'm saying that this is the original function here, and this is my inverse function. This is my original, this is my inverse, and I want to verify that they are in fact inverses, which means that I need to prove that f composed of its inverse is equal to just x, and if you do the inverse composed of the original function, that equals x. So you have to do two compositions and show that they're both equal to x. That's how you prove it. So the first one, I'll do f composed of its inverse, and I want to show that that equals x. So I'm going to start with f. So it's f of x is equal to negative 3x plus 6. Now I'm replacing the x with the inverse function, so that's negative 1/3 x plus 2. So that'll be negative 3, and where the x is, I'm replacing it with that function, so plus 2, and then plus 6. I'm going to distribute the negative 3 here. So negative 3 times negative 1/3. Remember, that's negative 3 over 1 times 1 over negative 3. So that's going to be negative 3 over 3, which is just equal to, oh, there's two negatives, so it'll be positive 1. So here I'm just going to get 1x. Then negative 3 times positive 2 is negative 6, and negative 6 plus 6 is 0. So I do get x on this side. Now I need to do it the same thing, but for the other way. So this time I'm going to do the inverse composed of the original function. So this time I'm starting with the inverse function. So the inverse function of x is equal to negative 1/3 x plus 2. If I plug in the original function, so compose that, I'm plugging in negative 3x plus 6. So that'll be negative 1/3 times negative 3x plus 6, and then plus 2. So distributing the negative 1/3, negative 1/3 times 3, remember that's just x. Negative 1/3 times 6, negative 1/3 times 6, you can put 6 over 1, it's be negative 6 over 3, so that equals negative 2. Then you have a plus 2 at the end. So these equal 0, so it equals x. Since this side equals x and this side equals x, I have proved that they are inverses. So therefore, which you can use these in math, sometimes we use the 3 dots in a triangle. We say therefore f of x and f of the inverse of x are inverses. They are inverses. Therefore, they are inverses. So we proved it. Let's prove one more. Verify that f and g are inverse functions. So I want to prove that f of x and g of x are the inverses of each other, which means that I need to show that if I take f composed of g of x, I get x, and if I take g composed of f of x, it also equals x. So I need to prove that. So this one I'm going to start with f. So f of x is the same thing as 8x to the 3rd power. Then plug in the g of x. That's x to the 1/3 over 2. So it'll be 8, replace the x with the x to the 1/3 over 2, and raise that to the third power. Then remember to distribute that exponent to each thing in the parentheses here. So you're going to get 8 times your power to a power 1/3 times 3 over 1 is 3 over 3. So you get x to the first over 2 to the third. 2 to the third is 2 times 2 times 2. So you get 8 times x over 8. This is like 8 over 1. So these 8 simplify to 1, you just get x. So this side is verified. I have to verify the other side as well. So I'm proving it by showing my work, basically. Just showing your work that both equal x. G of x comes first this time. So g of x is x to the 1/3 over 2. Replace that x with 8x cubed. So on the top, I'm going to have 8x cubed to the 1/3 all over 2. Power to a power, it's going to be 8 to the 1/3 x to the, remember that 1/3 times 3 is just x to the first over 2. Now you might be thinking, I don't know what 8 to the 1/3 power is. Well, you need to remember that 8 to the 1/3 is the cubed root of 8 x over 2. And the cubed root of 8 is 2. 2x over 2. The 2 simplify to 1. It equals x. So we have verified it for both sides. So therefore, they are inverses. F and g are inverse functions of one another. So if you think about this, 8x to the cubed, remember that's a cubic function, that's our little guy here. Well, if we reflected that over the line, it, this part would come up here, be like this instead. I can't remember exactly what it looks like. I'll show you later. Remember the vertical line test? We could tell if it was a function or not. Well, y equals x squared is a function because it passes the vertical line test. Well, the inverse of the function, you can tell if it's a function if it's the horizontal line. So, horizontal line test. If no horizontal line intersects the graph more than once, then the inverse is a function. So this one fails the horizontal line test, which means the inverse, the negative of this, would not be a function. Except for if we restricted the domain. So if it's the inverse of this would be, x equals y squared. So solve for y, you get square root of x equals y. So this is the inverse of y equals x squared. So we could make this a function as long as we said x was greater than or equal to 0. Then it would be a function because we would only have part of the graph. So that it's not a function as is. It doesn't pass the horizontal line test. But if we restricted the domain and said, okay, only take 0 and higher, now it's a function again. X cubed, though, that one, remember, looks like this. Now this one will pass the horizontal line test, so the inverse is a function. The inverse would actually be the cubed root of what, or the cubed root of x. So if it's cubed, the inverse is y equals cubed root of x. Since it is a function, I don't have to restrict the domain of that one at all, because you can take the cubed root of negative numbers, so that one's fine. So that's kind of what this slide talks about. We're going to start graphing squared and cubed functions in the next lesson. So let's see. We want to find the inverse of a power function. You do the same thing. This is y equals 1/4 x squared. So to find the inverse, you switch x and y. So you start by switching x and y. So you have x equals 1/4 y squared. Then you solve for y. So switch and then solve. So I need to get rid of this 1/4 first on the right side. So I'm going to multiply by its reciprocal of 4/1 on both sides. Multiply by 4/1. Maybe I shouldn't have thrown it in the middle there. That wasn't really, maybe put it here, 4/1. Because 4/1, this is going to be simplified to 1 on the right. I'm going to be left with y squared. Over here, I'm going to be left with 4x. Now to get y by itself, the inverse of squaring something is to take the square root. The square root of 4 is 2, and then you have the square root of x. The square root of y squared is y. So this is the inverse function for this. Y equals 2 square roots of x. The domain for this function has to be any x value greater than or equal to 0 because it's an even root. So it's only a function if you restrict the domain. So you can't have any negatives under there. We'll do this one quick too, just practicing finding the domain or the inverse, switch x and y, solve for y. So add 6 to both sides, get x plus 6 equals y to the 5th. If you have a 5th power, the reverse of that would be taking the 5th root. The 5th root and the 5th exponent would cancel each other out. So you'd have the 5th root of x plus 6 on the left, and that would equal y. So this would be the inverse function. Now, the 5th root is not an even root, so you don't need to worry about any negative numbers. So the domain for this one would be all real numbers. You can plug in anything you want there. I'm just curious to. Last one. Consider this function, determine whether the inverse of its function is a function, and then find its inverse. Okay, so consider this function. It's a even function with a positive a value. It's a quadratic, so it's going to look something like this. So if I think about the horizontal line test, because vertical line test tells me that the original function is a function, but the horizontal line test, since it crosses twice, that tells me that the inverse is not a function, and it's not a function unless I restrict the domain because it's squared. So if you switch the x and y, then you can find the inverse, and you'll see why you can't have negatives. So add 4 to both sides. We're trying to solve for y, so you get x plus 4 equals 2y squared. Divide everything by 2. This is going to be 1/2 x plus 2 equals y squared. Square root everything. You're going to have the square root of 1/2 x plus 2 equals y. So since you have a square root, the inverse of this, remember when we looked at the inverse, is going to look something like this. And so you can't have negatives under the exponent though, so you won't have that whole thing. The original function, whoops, the original function here was in blue. The inverse will look something like this. It has to be x's on the positive. If you have any x's on the negative, you would have to get rid of those to make sure that it's a function. So if for the inverse to be a function, you can only have one side of the whole thing. Otherwise, it's not a function. To find the inverse, switch x and y, solve for y. Remember that the domain and range then switch. To verify it, that's where you have to prove that when you do the composition of both back and forth, they both equal x. If the domain of the function equals x squared is restricted to only non-negative real numbers, then it is a function, because the domain or the inverse of y equals x squared is y equals the square root of x. So if you restrict the domain, because this one looks like this, but if you restrict the domain and only take half of it, now it is a function because it'll pass the vertical line test. Horizontal line test on the original is how you can tell if the inverse will be a function. So if it fails because it crosses twice, then the inverse of that function will not be a function. All right, that might be confusing. Hope you got it. This is the big part that you want to take away from today's lesson, finding the inverse and proving the inverse.